Okay, in weekly test 10, I kind of actually made a mistake, which is a bit stupid of me. I actually meant that the proton and the methyl group should have been on the same side. The problem is that I know that all of you are expecting it to be that, and I've never discussed what a 5-5 membered ring would do if they were on opposite sides like this. The reality is that if it were trans, and it can be, it's just not ideal. It's much more thermodynamically favored if they are cis to each other. If it is trans, it actually meant that the bottom face would be most accessible to MCPBA. However, because most of you wouldn't have known that, and so I marked this question very leniently. Most of you expected or just assumed that the methyl group pointing up would be the least sterically hindered side. It unfortunately wouldn't be, but nevertheless, I marked that correct. So long as you put the epoxide on one of the two sides, I would have given you the mark for that. It would have been okay. You just wouldn't have got marks if I hadn't explained, well, if you didn't put the epoxide on. So the answer should have looked something like that, technically speaking, but again, this was not something that I discussed with you. I wouldn't ask a question like this because we hadn't covered it in class. It was just a mistake I'd made in the question itself. The next one is less of a problem over here. This reaction doesn't go. It can't work because of the trans-diaxial relationship of those two protons on a Decalin system means that if this is axial up, then this carbon over here, axial up is well, up is axial. So this is actually equatorial. And because the bromine is equatorial, it needs to be in an axial position in order for an E2 elimination to occur. The proton and the bromine have to be anti-periplanar to each other. And because it's equatorial, it can't ever do that. So E2 elimination is impossible, since Br is equatorial. So that would be the answer to that question over there. All right. I did see some weird answers to that, but just check. Some people were doing substitutions and putting in some rather strange things. Yeah, this won't act as a nucleophile, so it's too bulky. It's highly unlikely that would happen. Okay, here we have to draw both chairs. It's important that we're able to do that. So I'll draw this. I'm working in pen, it's not really the most ideal. So this is the one. Make sure that you work, that you count round in a sort of clockwise direction and do it the same. If I put over here, it's pointing up. So it's axial, and we go 2 across. Up over there is going to be axial for the methyl group, and then over here, the up will be equatorial for the chlorine group over there. So then the next one, we can do exactly the same chair. We just need to move things across. Fix this up, make it neat. Okay, so we just need to move them one across. So I'll put the over here, it's going to be equatorial up for the isopropyl group, and over here the methyl group will be sitting equatorial up, and then the chlorine over here will be axial up on that. And so this one would be preferred because large groups are equatorial. Most of you got that very nicely, so that wasn't a problem. The last question was the one that we're really having to apply a lot of the different methods that you know. The issue here is that if you're going to use an acylation of an enolate method, means that we're either going to form this bond or this bond. There's two, well, not two, there's actually a number of different ways that you could actually do this. But a lot of you had the idea of, as an example, you're going to form that bond over there. So you want to form this enolate, sorry, minus, sorry about that. You want to form that enolate, and then you need to have a reactive partner. So what you did is you added a chlorine on over there. The problem with this is methyl chloroformate. This would react with oxygen. acid chlorides are going to react with oxygen, so they would acylate. So this wouldn't work over here. The solution to this kind of thing would be to use a non-enolizable the ester equivalent. So this is actually a carbonate, but dimethyl carbonate. So that's one would work. So one thing that you could have done is, for instance, you could have created this with LDA first in one step. Then you could have added this and it would have worked. Another option is you could have done something. If you wanted to have used this, then you could have done it with a TMS, silyl enol ether. You could have done that. And then likewise, you could have made the disconnection at this point over here. So then your acylating partner would have been something like this. So there would be some leaving group on over here. If it's a chlorine, then we need to make sure that the enolate partner that we use can't be like a lithium enolate, because the chlorine will go to the oxygen. So then it needs to be a silyl enol ether variation. And because this side over here is a part of an ester, it can't be an azo enolate or an enamine. If this is an ester, that's okay because it's a non-enolizable ester, but then we must make the lithium enolate of this and get it to react with that. So that's really, basically 4 different answers that you could have had with this. If you broke on this side, you could have used a methyl ester of this, or an ethyl ester, whatever, and a lithium enolate on this part. You could have used an acid chloride of this, but a silyl enol ether of this part. If you broke over here, you would have to use the methyl ester and a lithium enolate, or you could use the acid chloride, but then you must use the silyl enol ether. So those are the 2 options there.